पड़ेगा आपको। हाँ जी जब इसमें दिक्कत आती है, इसका प्रोसेसर भी सपोर्ट नहीं करता है ये। अब देखिए इसमें आपको स्पीकर भी लगाना पड़ेगा, तो सॉरी माइक। कैमरा तो आ गया, बट सर आपकी भी ऑडियो आनी चाहिए ना। सर फोटो तो आ रही है, बट आपने कोई माइक ही नहीं कनेक्ट किया है ना, वो माइक आपको कनेक्ट करना पड़ेगा, तो फिर इंटरेक्शन कैसे होगी सर, ये देखिए। सर अभी करवा दीजिए ना, बिकॉज अभी इंटरेक्शन होगी तो फिर आपकी साइड से कैसे।
field. So it's important also again that if you're going into a field, you might be going to or traveling to different states also with an optical fiber machine. So it's important. So you should have a battery backup so that
Okay. Welcome you all. So अभी we are starting now with an optical fiber splicing practical. So सबसे पहले I want to show you that कि जिस optical fiber से हमने वो optical fibers निकाली हैं वो कुछ इस तरह से material है। ये बहुत ही solid material है made up of plastics। ये एक्चुअली इसके अंदर सिरेमिक्स पूरी होल्स हैं जिसको कंट्रोल करके रखा जाता है ताकि कोई भी एटमॉस्फेरिक प्रेशर या फिर कोई भी बर्डन अगर इसके ऊपर हो तो प्रॉब्लम ना करे ऑप्टिकल फाइबर्स को। तो ऑप्टिकल फाइबर्स इसके अंदर सिक्योर रहती हैं। तो ये जो आप ऊपर देख रहे हैं, मैंने कल भी बताया था, अगर हम ऑरेंज कलर देख रहे हैं तो इट मीन्स इट्स अ मल्टी मोड फाइबर। अगर यही कवर वो येलो कलर का होता तो इट्स एन सिंगल मोड फाइबर। तो मल्टी मोड फाइबर के लिए हमने केबल्स करी हैं, और जो ये केबल ऑप्टिकल फाइबर है उसके अंदर कुछ इस तरह की ऑप्टिकल फाइबर्स थी सारी। तो आप ये स्ट्रैंड्स देख सकते हैं सारे, ये रिबन फाइबर है एक। हम रिबन क्यों कहते हैं, क्योंकि आप देख सकते हैं कि जो ऑप्टिकल फाइबर्स है वो इन द फॉर्म ऑफ रिबन है सारी यहाँ पर। तो ये डिफरेंट डिफरेंट कलर्स की हमारे पास ऑप्टिकल फाइबर्स हैं यहाँ पे बहुत सारी। तो हमने क्या करना है, इसमें से कोई भी पर्टिकुलर पॉइंट से हम कोई भी एक ऑप्टिकल फाइबर यहाँ से अलग कर सकते हैं इसको। चाहे तो हम इस मशीन में रिबन फाइबर को एक साथ भी कर सकते हैं, पर राइट नाउ व्हाट वी आर डूइंग इज कि हम सिर्फ और सिर्फ कोई एक ऑप्टिकल फाइबर अलग कर रहे हैं। और उससे पहले मैं आपको दिखाना चाहता हूँ, इसके ऊपर एक कोई सिल्वर सी डिज़ाइन से ये लगा हुआ है इस पर। सो मैं आपको ये निकाल के दिखाता हूँ। इट्स जो आप ये देख रहे हैं यहाँ पे जो ये अलग से निकल रहा है, इट्स एक्चुअली सिलिका जेल। सिलिका जेल हम लगाते हैं कभी भी बफर और ऑप्टिकल फाइबर को पकड़ के रखने के लिए, क्योंकि जो हमारी ऑप्टिकल फाइबर है वो ग्लास की बनी हुई है, वो कभी भी स्लिप आउट हो सकती है। तो वो रोटेशन में पूरी की पूरी सिलिका जेल उसके ऊपर कवर अप रहती है ताकि उसकी स्ट्रेंथ और पकड़ बनी रहे एक साइड पर। तो दिस इज द ऑप्टिकल फाइबर जो हम यूज़ करने वाले स्लाइसिंग के लिए। तो मैं कोई भी एक कलर की ऑप्टिकल फाइबर बाहर निकाल लेता हूँ इसमें से। सो और आपको सबसे पहले तो इस चीज़ पे ध्यान रखना है कि कोई भी ऑप्टिकल फाइबर आपके हाथ में ना जाए। तो अगर आप सबसे पहले कभी भी फर्स्ट टाइम कर रहे हैं तो यू शुड वियर अ ग्लव्स। वी आर एक्सपर्ट्स, हम काफ़ी टाइम से कर रहे हैं तो वी नो दैट कि कब किस साइड पे हाथ लगाना है और कहाँ पे नहीं लगाना है। सो आई हैव टेकन अ ऑप्टिकल फाइबर आउट। तो इस ऑप्टिकल फाइबर को हम यहाँ पे स्प्लाइस करेंगे। ठीक है, स्प्लाइस करने से पहले मैं आपको कुछ इंस्ट्रूमेंट्स के बारे में अच्छे से बताना चाहता हूँ ताकि आपको हर एक चीज़ के बारे में नॉलेज हो। सबसे पहले जो मेन इक्विपमेंट है हमारा ऑप्टिकल फाइबर स्प्लाइसिंग मशीन, इसके बारे में देखते हैं। हियर वी आर हैविंग अ स्क्रीन जो कि टच स्क्रीन है हमारे यहाँ पे सब कुछ डिस्प्ले होता है, हमारी एक्स वाई एक्सेस, हमारे जितने भी कंट्रोल पैनल्स के बटन है वो यहाँ पे शो होते हैं। इंस्टेड ऑफ दैट ऑल्सो हमारे पास कुछ एक्सटर्नल कीज बटन भी हैं यहाँ पे, जैसे आप देख सकते हैं यहाँ पे क्रॉस के लिए है, देन वी हैव एन ओ मीन्स फॉर योर ऑन बटन, एंड देन यहाँ पे है ऑन ऑफ के लिए जो आपकी मशीन ऑन ऑफ करेगा। देन वी हैव टू बटन सिमिलर, यहाँ पे दो बटन है, ये एक्चुअली हीट चैम्बर्स के लिए हैं जो कि हमारे पास यहाँ पे प्रेजेंट है। ये हमारा हीट चैम्बर होता है जहाँ पे हम स्लीव्स को हीट करते हैं इसके अंदर। तो ये हमारा था, और मैंने पहले भी बताया ये हमारा पावर पैनल होता है जहाँ पे हम पावर स्विचेस को ऐड करते हैं इसके अंदर। नेक्स्ट वी हैव अ बैटरी एंड द बैक साइड जो कि 12 आवर्स तक इसके अंदर चल सकती है। तो वो मैं आपको बाद में खोल के दिखाऊंगा किस तरह की बैटरी होती है इसमें। सो फर्स्ट ऑफ ऑल जो हमारा चैम्बर होता है जहाँ पे हमारी स्लीविंग्स होती हैं वो कुछ इस तरह से होता है अंदर से। तो मैं ये कवर है जो मैंने लेग को ओपन किया है इसके अंदर, आप यहाँ पे देख सकते हैं पूरा इंस्ट्रूमेंट रेडी है। यहाँ पर हमें दो मैग्नेटिक क्लैंप्स यूज़ करने होते हैं, यहाँ पे प्लेस करने होते हैं ऑप्टिकल फाइबर्स के साथ। और जो आप ये ब्लू पोर्शन देख रहे हैं इसको हम वी ग्रूव के नाम से जानते हैं। इसमें क्या है, बहुत छोटे छोटे कट से लगे हुए हैं जिसमें हम ऑप्टिकल फाइबर को प्लेस करते हैं इसके अंदर। तो जैसे ही वो ऑप्टिकल फाइबर प्लेस होंगी इसके अंदर वो अपने आप एडजस्ट होकर अपने आप आग में स्प्लाइस कर देते हैं मशीन। तो ये हमारी स्प्लाइसिंग के लिए होगा यहाँ पे। और ये जो दो आपको रॉड्स दिखाई दे रही है यहाँ पे जो सिल्वर कलर की है ब्लू के साथ, दे आर द इलेक्ट्रोड्स जो कि हार्क आपका फ्यूजन वहाँ पे क्रिएट करते हैं, हाई इलेक्ट्रिसिटी वोल्टेज प्रोड्यूस करते हैं जिसकी वजह से वो आग वहाँ पे प्रेजेंट होता है। तो ये हमारा स्प्लाइसिंग के लिए यूज होगा। एंड देन द सेकेंड पार्ट विल बी आर हीट स्लीव्स चैम्बर्स। हमारे पास साइमल्टेनियसली हम दो चैम्बर्स को एक साथ हीट अप पे लगा सकते हैं, मतलब दो स्लीव्स को एक साथ कर सकते हैं। क्योंकि अगर हम रिबन फाइबर को कर रहे हैं तो रिबन फाइबर में कंटेन मोर देन 12 फाइबर्स, तो एक एक फाइबर को करने के लिए 30 to 90 सेकंड्स का टाइम लगता है, तो वो बहुत ज़्यादा टाइम कंज्यूमिंग होगा। इसलिए वी हैव टू डिफरेंट काइंड्स ऑफ चैम्बर्स ओवर हियर। तो इसको यूज़ करना बहुत ही सिंपल है, हमने बस यहाँ पे फाइबर को ला के रखना है स्लीव्स के साथ और बस इसे बंद कर देना है। जैसे ही बंद करेंगे मशीन ऑटोमेटिकली डिटेक्ट कर लेती है उस ऑप्टिकल फाइबर को और वो वहाँ पे हीट अप करना शुरू कर देती है। तो ये हमारी मेन मशीन के बारे में बात हुई। नेक्स्ट वी आर हैविंग इज आर क्लीवर। सो क्लीवर जो आप ये किट पूरी खरीदते हैं ये पूरी एक ही कंपनी की रहती है, आप ऐसा नहीं है कि डिफरेंट डिफरेंट खरीद सकते हैं इसमें। तो ये आप अगर डिफरेंटली खरीदते हैं इक्विपमेंट्स तो आपको बहुत कॉस्टली पड़ते हैं इसमें, तो इट्स बेटर कि आप इसको एक किट के अंदर ही लें इसमें। सो वी आर हैविंग अ क्लीवर ओवर हियर। क्लीवर के लिए बहुत सिंपल से स्टेप है जो आपको फॉलो करना है इसके अंदर। फर्स्टली आपको जब भी यूज़ करना है क्लीवर को तो पहले आपको इसको सीधा खोल के रखना है और ट्राई नॉट टू टेक इट ऑन योर पाम, मतलब आप पाम पे कभी भी इसे यूज़ ना करें क्योंकि ये अनस्टेबल है यहाँ पे, तो ऑप्टिकल फाइबर कभी भी प्रॉपर्ली नहीं कट होगा इसके अंदर। तो ट्राई टू मेक इट ऑन अ स्टैंड जो कि आपका एकदम सॉलिड मटेरियल जगह हो कहीं पे, तो आप वहाँ पे यूज़ करें इसको। तो जब भी आप इसे यूज़ कर रहे हैं तो आपको हमेशा यहाँ से ऑप्टिकल फाइबर मैग्नेटिक क्लैंप ला के रखना है यहाँ पे, और जैसी ऑप्टिकल फाइबर होगी वो यहाँ तक कुछ अप्रॉक्सीमेटली आएगी इसमें। तो द सेकेंड स्टेप विल बी आपको ब्लेड को मूव करना है आगे की तरफ वहाँ पे। जब ब्लेड अपनी पोजीशन पे है आपने इसको बंद करना है यहाँ से, एंड देन यू हैव टू पुश इट बैक। तो इस तरह से हमारी मैग्नेटिक जो हमारी केबल है वो कट हो जाती है इसके अंदर। तो ये प्रोड्यूस करेगी हमारी 90 डिग्री पे एग्जैक्ट कट हमारा उसके साथ। एंड देन द फर्स्ट स्टेप जो हमारा सबसे पहले आता है, जो मैंने बात करी थी, वो थी स्ट्रिपिंग की। हमारे लिए सबसे इंपॉर्टेंट है कि फाइबर की ऊपर की जो भी हमारी केबल उसके ऊपर लगी हुई है, जो भी बफर लगा हुआ है, वो हमारी यूज़ का नहीं है बिल्कुल भी। तो वी वांट कि वो सारी केबल्स हमारे रिमूव कर सके उसके ऊपर। अगर हम सीजर यूज करते हैं तो इट इज़ वेरी डिफिकल्ट कि हम सीजर से एक एक पॉइंट को रिमूव कर पाए वहाँ से, और हो सकता है कि हम एक्सटर्नल प्रेशर को ज़्यादा लगा दें उसके ऊपर, तो हो सकता है वो जो हमारी ऑप्टिकल फाइबर है वो कहीं से डैमेज हो जाए उसके अंदर। इसलिए वी आर यूजिंग अ थर्मल स्ट्रिपर जो कि स्पेशली डिजाइंड है इसी हिसाब से कि वो सिर्फ और सिर्फ बफर को मेल्ट करता है इसके अंदर। तो इसको यूज भी करना बहुत आसान है, प्लस इसकी मेंटेनेंस थोड़ी सी हमें रखनी पड़ती है साथ साथ, नहीं तो इसकी डिग्रेडेशन बहुत जल्दी होती है। तो व्हाट वी हैव टू डू इज, सबसे पहले हमें ऑप्टिकल फाइबर मशीन ऑन करनी होती है इसके लिए। चाहे इसको ऑन करने के लिए तो आई एम स्विचिंग ऑन द ऑप्टिकल फाइबर मशीन, मैंने बस वो बटन होल्ड करके रखा है एंड इट्स स्टार्टिंग नाउ। तो यू कैन सी द मैन्युफैक्चरर नेम ओवर हियर and it produces beep sound. Beep sound means the machine is calibrated to the settings जो हमने last time set करी थी. If you are not hearing that beep sound, it means the calibration is not done and you have to do it again manually. So it is all set to do the splicing now and I have to start it. आपने देखा जैसे मैंने इसे स्टार्ट किया तो यहाँ पे एक येलो लाइट ब्लिंक करने लगी। इट्स शोइंग मी द टेम्परेचर की टेम्परेचर वेरिएशंस हैं यहाँ पे, आप देख सकते हैं L फॉर लो एंड देन द मीडियम पॉइंट्स, इंटरमीडिएट एंड द हाई टेम्परेचर। तो मैं टेम्परेचर यहाँ पे टेम्परेचर की प्रेस करके उसको एडजस्ट कर सकता हूँ। तो पहले हम इसे ऑन करते हैं नीचे से। जैसे ये मोड ऑन हुआ इट स्टार्ट शोइंग कि वो हीट हो रही है वहाँ पे, एंड देन मैं इसका टेम्परेचर धीरे धीरे बढ़ा देता हूँ ताकि मेरे लिए बफर को इरेज करना और भी ज़्यादा ईजी हो। तो सबसे पहले इसको यूज़ करने के लिए मुझे सबसे पहले इसको अंदर से साफ़ करना होगा। तो यहाँ पे अंदर हमारे पास मैग्नेटिक क्लैम्प के लिए दोबारा से यहाँ पे जगह है ताकि वो प्लेस रहे और एक्यूरेट ज़्यादा रहे हमारा ऑप्टिकल फाइबर। जब भी ऑप्टिकल फाइबर प्लेस करते हैं हमें स्टार्टिंग में कुछ कह सकते हैं कि ध्यान में रख के ऑप्टिकल फाइबर को लेंथ चूज करना होता है कि वो यहाँ से आगे ना बढ़े ज़्यादा। अगर वो यहाँ से स्ट्राइक करेगी तो वो बेंड हो जाएगी ऑप्टिकल फाइबर, तो उस हिसाब से हमें प्रॉपरली पूरा देख के करना पड़ता है। तो यूज़ करने का तरीका है बस जैसी मैग्नेटिक क्लैम्प प्लेस किया यहाँ पे इसे क्लोज कर देंगे हम और थोड़ी देर इसे प्रेस करके रखेंगे, देन वी स्टार्ट पुशिंग इट। तो जैसे वो पुश होगा जितनी भी ऑप्टिकल फाइबर पे हमारी जो भी आगे बफर लगा होगा वो सब कुछ रेसिड्यू इस पे रह जाएगा और बाकी ऑप्टिकल फाइबर प्लेन हम मैग्नेट क्लैम्प से निकाल सकते हैं। तो उसी के बाद हम बाकी के स्टेप्स फॉलो करेंगे। तो ऐसे ही आपको मैं करके दिखाता हूँ इस पे एक ऑप्टिकल फाइबर के लिए प्रैक्टिकल। और ये जो कलर्स हैं, मैं कलर्स के बारे में मैं आपको बाद में बताऊंगा कि हमारे पास डिफरेंट डिफरेंट कलर्स की क्यों है ऑप्टिकल फाइबर। ये हमें जो कोर इसका आउटर बफर जैकेट होता है सिर्फ वो ही बताता है हमें कि मल्टी मोड है या सिंगल मोड। ये कलर्स जो अलग अलग है ब्लू, ब्राउन, वाइट, ग्रे, ये हमें कलर्स नहीं बताते हैं कि इट्स अ मल्टी मोड और सिंगल मोड। ये एक्चुअली कलर है सिर्फ रिकॉग्नाइज करने के लिए कि डिफरेंट टाइप्स ऑफ केबल डिफरेंट प्रोसीजर्स के लिए यूज की जाती है, प्लस डिफरेंट पावर कैरी करती है ये। तो इसलिए हम कभी भी जैसे सपोज मैं ब्लू वाली को अगर ज्वाइन करवा रहा हूँ अभी, तो मैं ब्लू वाली को सिर्फ और सिर्फ ब्लू वाली के साथ ही स्प्लाइस कर सकता हूँ। इफ आई एम स्प्लाइसिंग विद एनी अदर कलर तो मेरे लिए बहुत ज़्यादा डिफिकल्ट होगा इस चीज़ को कि उनको प्रॉपरली अलाइन कर पाना, प्लस उनके लिए लॉसेस कम लेके आना। तो वी आर नॉट डूइंग अ इंडस्ट्रियल प्रैक्टिकल, वी आर जस्ट परफॉर्मिंग अ लैबोरेटरी प्रैक्टिकल। तो मैं इसी एक वायर को आपस में ही कोइंसाइड करके एक सर्कुलर गेज बनाऊंगा इसके लिए। सो फॉर दैट सबसे पहले मुझे ऑप्टिकल फाइबर को प्लेस करना है एक मैग्नेटिक लैम्प पे ताकि मेरी एक्यूरेसी स्टार्टिंग से ही रहे इसके अंदर। तो आई एम यूजिंग मैग्नेटिक लैम्प्स ओवर हियर। इनको यूज़ करने का तरीका भी बहुत आसान है, कुछ डिफिकल्ट नहीं है। इट कंटेन्स अ मैग्नेटिक इनसाइड और एक लैम्प लगा हुआ है जो उसको क्लोज कर देता है। तो मुझे जो यहाँ पे ये ट्रे बनी हुई है उसके अंदर ऑप्टिकल फाइबर को प्लेस करना है उसमें। सो बी श्योर कि वो सिर्फ और सिर्फ उसी बीच में रहे और वो कहीं और मूव नहीं कर रही है। इफ इट स्टार्ट मूविंग तो आपकी एक्यूरेसी फिर से वो खराब हो जाएगी उसमें। एंड बी श्योर कि आप पर्टिकुलर हाइट की ही ऑप्टिकल फाइबर बाहर निकाल रहे हैं जो कि स्ट्रिपर में एडजस्ट हो सकती है। सो दिस इज हाउ वी हैव टू पुट एन ऑप्टिकल फाइबर इन अ क्लैम्प। सिमिलरली मैं सेकेंड एंड पे भी बिल्कुल ऐसे ही करूँगा, बट हम सबसे पहले फर्स्ट एंड प्रिपेयर कर लेते हैं। तो फर्स्ट एंड को प्रिपेयर करने के लिए जैसे ही हमने इसको इसमें लगाया देन वी नीड अ थर्मल स्ट्रिपर। तो हमारा ये थर्मल स्ट्रिपर है जो कि हीट अप हो चुका है। तो विल प्लेस अ मैग्नेटिक क्लैम्प ओवर हियर। नाउ यू सी जो मैं आपको बता रहा था अगर मैं एडजस्ट नहीं करता इसको प्रॉपर्ली तो अब ऑप्टिकल फाइबर यहाँ पे स्ट्राइक कर रही है। तो मैग्नेटिक क्लैम्प की जो प्लेस है जितनी आनी चाहिए उससे ज़्यादा है और यहाँ पे ऑप्टिकल फाइबर पूरी नहीं आ पा रही है। तो आई हैव टू री एडजस्ट अगेन। तो मुझे थोड़ा सा इसे पीछे निकालना पड़ेगा और ध्यान रखिए जब भी आप कभी एक बार ये ऑप्टिकल फाइबर का प्रोसेस शुरू कर देते हैं, अगर स्ट्रिपिंग हो चुकी है तो आप बार बार मैग्नेटिक क्लैंप्स ना खोलें। उससे क्या है कि आपकी जितनी एडजस्टेबल हाइट है वो एडजस्ट रहती है आपकी ऑप्टिकल फाइबर मशीन के साथ, तो मशीन के साथ वो एडजस्टेबल रहे तो आप क्लैंप वहीं पर ही बंद रखिए हमेशा, तभी एक्यूरेसी ज़्यादा रहेगी उसमें। सो वी हैव डन। तो हम यहाँ पे देखते हैं अभी भी इसे अभी भी थोड़ा सा ज़्यादा है। और ये भी ध्यान रखिए कि बहुत ज़्यादा छोटी भी ना हो, क्या क्योंकि फिर बाद में क्लीविंग पे उसको बहुत प्रॉब्लम आती है, क्लीविंग पे वो डायरेक्टली कट नहीं कर पाता उसको। तो हियर वी हैव, तो हमने इसको प्लेस कर दिया इसके अंदर। तो अब कुछ सेकंड्स के लिए हम इसको इसी मेंटेन रखेंगे इस प्रेशर को यहाँ पे। तो थोड़ा सा प्रेस करना पड़ता है इसको, देन स्लोली स्लोली हमें इसे अपार्ट करना पड़ता है। इसको क्लीन करने के लिए आई एम यूजिंग अ सिंपल ब्रश, जो पेंटिंग ब्रश आप घरों में भी यूज़ करते हैं पेंट्स के लिए, छोटा वाला ब्रश कोई भी यूज़ कर सकते हैं इसको क्लीन करने के लिए। इट्स ओनली अ बफर, तो कोई प्रॉब्लम नहीं है अगर ये किसी के हाथ पे लग भी जाता है तो। इट्स जस्ट अ प्लास्टिक कोटिंग। तो ये अब धीरे धीरे रिमूव होने लग गया है यहाँ से। इट्स नॉट पॉसिबल कि आप एक ही बारी में उसको पूरा स्ट्रिप कर पाएँ, तो इट विल टेक सम टाइम। तो यहाँ पे ये स्ट्रिप हो चुका है। सो आफ्टरवर्ड दिस इज हाउ इट विल लुक लाइक। मैं ब्लैक शीट पे रखता हूँ थोड़ा सा ताकि आपको क्लियर हो। तो आप देख सकते हैं ये क्लैडिंग जो ब्लू कलर था ऑप्टिकल फाइबर का वो उतर चुका है उससे, और सिर्फ क्लैडिंग और कोर बाहर आ चुका है उसके ऊपर से। तो इसी चीज़ को हमने स्प्लाइस करना है। अभी डोंट नो कि ये एग्जैक्ट ऊपर से जो टॉप है ये कहीं जगह स्ट्राइक किया होगा, इधर उधर गिरा होगा, तो हो सकता है वो ब्रेकेज आई हो उसमें काफ़ी ज़्यादा। तो वी वांट कि ये 90 डिग्री पे कट रहे ताकि ये प्रॉपरली स्प्लाइस हो सके। तो विल बी डूइंग द पार्ट फॉर क्लीनिंग नाउ। अगर आप चाहें तो इसे एक बार साफ कर सकते हैं, बट आई मेंशन कि अगर आप फर्स्ट टाइम कर रहे हैं तो साफ इसे थोड़ा ना करें आप ज़्यादा, क्योंकि आप डैमेज कर सकते हैं उसको। तो यू शुड बी वेरी केयरफुल जब भी आप इसको कोर को हैंडल कर रहे हैं, क्योंकि ये ग्लास है और इसकी सेंसिटिविटी बहुत ही ज़्यादा कम है। तो आप जैसे ही इसको पकड़ेंगे तो कभी भी ये टूट सकती है बीच में से, तो स्लाइसिंग के टाइम पे बहुत प्रॉब्लम आएगी इसके लिए। तो योर सेकेंड स्टेप देन कि आपको मैग्नेटिक लैंप्स प्लेस करना है इसके अंदर प्रॉपरली पूरा, एंड देन ब्लेड को आपको आगे की तरफ मूव करना है इसके अंदर। तो ये जैसे कि रहेगा आपको बिल्कुल इसी तरह इसमें प्लेस करके रखना है, एंड देन आपको आराम से इसको बंद कर देना है। यू विल हर्ड अ लॉक, आपको ऐसे नहीं ज़बरदस्ती बंद करना है, आपको लॉक सुनाई देगा, लॉक लग चुका है उसके ऊपर। अब जैसे ही लॉक लगा कोई भी एक्सटर्नल प्रेशर उसके ऊपर अप्लाई नहीं करना। आपको ये सेकंड स्टेप जो दोहराना था वो था ब्लेड को बस मूव कर देना है ऑपोजिट साइड को। जैसे ही ये मूव हुआ वी हैव एन क्लीव्ड ऑप्टिकल फाइबर ओवर हियर। तो आप देख सकते हैं कि ऑप्टिकल फाइबर एक स्ट्रेंथ तक कट चुकी है अपने आप ही वहाँ पे, और ये एडजस्टेबल स्ट्रेंथ अपने आप ही ऑप्टिकल फाइबर मशीन के हिसाब से है। तो जो बाकी बचा हुआ मटेरियल है इसे ध्यान रखें कि आपको डिस्पोज करना ज़रूरी है, क्योंकि ये चीज़ है अगर किसी के भी हाथ में लग जाती है या फिर चली जाती है तो इट विल कॉज अ वेरी सीरियस हेल्थ प्रॉब्लम्स। तो इसको डिस्पोज करने के लिए मैं यहाँ पे टिश्यू पेपर का यूज़ कर रहा हूँ अभी। इफ यू आर इन एन एयर और समथिंग, आपको वहाँ एक टिश्यू पेपर यूज़ नहीं करना है, क्योंकि वहाँ ये उड़ भी सकती हैं चीज़ें। तो जो भी मेरा रेसिड्यू होगा वो सब कुछ मैं इसके ऊपर प्लेस कर रहा हूँ यहाँ पे, ताकि मेरे को आसानी हो यहाँ से बाद में इसको आसानी से डिस्पोज करने के लिए। तो हियर आई हैव द फर्स्ट क्लैंप। अब मैंने क्या करना है, इस क्लैंप को इस मशीन के अंदर प्लेस करना है। तो मेरे पास क्लैंप में यहाँ पे आप देख सकते हैं 2 होल्स हैं। सिमिलरली मेरे पास यहाँ पे मशीन में भी 2 होल्स यहाँ पे बने हुए हैं, 2 स्ट्रॉस हैं यहाँ पर, जिसके अकॉर्डिंगली वो फिट होगा जिस पोजीशन पे आना है उसको। तो मैं यहाँ पे देखता हूँ, तो इट्स नॉट फॉर दिस साइड, सो इट फॉर दिस वन। तो मैं यहाँ पे इसको प्लेस कर देता हूँ, और बहुत ही आराम से रखें ताकि ये ऑप्टिकल फाइबर ब्रेक ना हो बिल्कुल भी। तो ये आपका पहला क्लैंप इसके अंदर प्लेस हो चुका है इसमें। तो मैं इसे एक बार बंद करके देखता हूँ कि हाउ इज इट लुकिंग। तो आप यहाँ पे देख सकते हैं स्क्रीन के ऊपर, स्क्रीन पे बहुत ही क्लियरली आपको ऑप्टिकल फाइबर यहाँ से दिखाई देगी, और उसका क्लीन एजेस भी दिखाई देंगे जो कट हुई है हमारे लिए। नहीं देखिए
थोड़ा सा टिप दिखा दीजिए।
सो आई थिंक अब आपके लिए विजिबल होगा यहाँ पे। आप यहाँ पे देख सकते हैं कि यहाँ पे आपको ऑप्टिकल फाइबर बाहर निकलती हुई दिखाई दे रही है कैमरास में। तो इसके बाद आपके पास यहाँ पे कुछ वेरियस बटन्स हैं, स्टार्ट, आर्क, क्रॉस, मेन्यू, योर बैटरी लोकेशंस, और ये हीट इंडिकेटर्स दिखा रहा है जो आपके स्लीव्स के टाइम पे काम आती हैं। तो ये चीज़ें हैं आपकी जो हमने यूज़ करनी है सारी। तो अभी हम स्प्लाइस वगैरह कुछ नहीं करेंगे क्योंकि हमारी ऑप्टिकल फाइबर अभी सिर्फ एक है, हमें ऐसे ही सेकेंड एंड भी प्रिपेयर करना है। बट बिफोर स्टार्टिंग द सेकेंड एंड, जो मैंने आपको बताया था कि हमें स्लीव सबसे इंपॉर्टेंटली इसके अंदर डालनी है पहले। तो दिस इज़ द काइंड ऑफ स्लीव जो मैंने आपको दिखाई थी। इसमें रेजिन है, एक मेटालिक रॉड है और प्लास्टिक का बना हुआ है ये पूरा। तो एक एंड पे मैं इसको ऑप्टिकल फाइबर के अंदर डाल देता हूँ यहाँ से, और इसको नीचे तक ले जाता हूँ। तो अभी मुझे ये स्लीव यूज़ नहीं करनी है, मुझे बस एंड प्रिपरेशन के लिए रेडी करना था उसको। सिमिलरली अब मैं इसे भी वैसी ही प्रिपरेशन करनी है इसकी। तो हम इसे भी एक बार स्ट्रिप करते हैं ध्यान से। थोड़ा सा यहाँ पे प्रेशर लगा के रखना पड़ेगा ताकि वो हीटिंग प्रॉपर हो इसमें। देन उसे रिमूव करना स्टार्ट करें। आपके लिए ज़रूरी है कि आप इसे बहुत ही धीरे से करें, क्योंकि ऑप्टिकल फाइबर के टूटने का दर यहाँ पे भी होता है पूरा। नाउ अब इसे क्लीव करते हैं, दोबारा से वही सेम स्टेप हमारा फॉलो अप रहेगा। ब्लेड को दूसरी साइड पे मूव करके एंड इसे लॉक कर दिया। लॉक करने के बाद बस इसे मूव कर दें ऑपोजिट साइड पे ब्लेड को। देन वी हैव अ क्लीव्ड ऑप्टिकल फाइबर। तो हमारे पास ये ऑप्टिकल फाइबर दूसरा एंड भी रेडी है इसमें। तो हम इसे ओपन करके इस ऑप्टिकल फाइबर को प्लेस कर देते हैं दूसरी ऑप्टिकल फाइबर के एडजेसेंट। तो अब हमारी दोनों ऑप्टिकल फाइबर रेडी हैं। वी हैव प्लेस बोथ द ऑप्टिकल फाइबर्स। अब आप यहाँ पे देख सकते हैं दोनों में, यहाँ पे आपको ऑप्टिकल फाइबर्स जो दिखाई दे रही हैं, आप देख सकते हैं दोनों ऑप्टिकल फाइबर्स के पास, दोनों के पास क्लीन एजेस हैं, और ये दिखा रहा है कि कितनी एडजस्ट अभी वो अलाइन नहीं है आपस में। तो हो सकता है कि वो रिबन फाइबर के वी ग्रूव की वजह से, जिसमें बहुत सारे सेक्शंस हैं, वो किसी एक सेक्शन में जा चुकी है अंदर। बट मैं उसे ठीक ना करके मैं आपको दिखाना चाहता हूँ, अगर हम इस पर भी स्प्लाइस करते हैं तो उसका रिएक्शन क्या होता है। तो इफ आई प्रेस स्टार्ट, अगर कभी भी आपको स्प्लाइस करना है तो फर्स्टली आई प्रेस द स्टार्ट बटन। तो अब आप देख सकते हैं कि ऑप्टिकल फाइबर अपने आप मूव हो रही है, एंड मूव होते होते एक ऑप्टिकल फाइबर उसके पैरेलली अपवर्ड्स मूव हो गई है। तो इट्स शोइंग कि वो कितना एक्स और वाई एक्सिस पे लॉसेस मेरे को दिखा रहा है। तो यू कैन सी यहाँ पे 1.0 dB का मेरे को कुछ लॉस आ रहा है, एंड ऑन द अदर साइड ऑन द वाई एक्सिस आई हैव अ लॉस ऑफ नियर अबाउट 9.0 dB, जो कि बहुत ज़्यादा है। 1.0 इज बेरेबल कि मैं इतना एडजस्ट कर सकता हूँ, बट 9.0 इज वेरी डिफिकल्ट। तो जो ऑप्टिकल फाइबर ये ऊपर जा रही है, मुझे इसे थोड़ा ठीक करके रखना पड़ेगा। तो आई विल रीसेट, हम रीसेट करते हैं इस मशीन को, एंड देन वी ओपन द मशीन ओवर हियर। एंड अब मुझे थोड़ा सा मैन्युअली काम करना पड़ेगा ताकि मुझे पता लग जाए कि वो आपस में एडजेसेंट है। ये बहुत सिंपल है, मुझे ऑप्टिकल फाइबर के ऊपर ध्यान ना देके मुझे स्क्रीन के ऊपर ध्यान देना है, ताकि मुझे पता लग जाए कि ऑप्टिकल फाइबर कहाँ को मूव हो रही है। तो आई विल लुक इट इन टू द स्क्रीन, और जिस ऑप्टिकल फाइबर को मेरे को मूव करना है, मैं उसको दूसरे वी ग्रूव में डाल दूंगा वहां से। तो आप स्क्रीन में साथ साथ देख सकते हैं जैसे मैं मूव कर रहा हूँ। तो यहाँ पे एक्चुअली एक ऑप्टिकल फाइबर टूट चुका है, तो उसकी वजह से वो खराब आ रहा है पूरा। तो यू कैन सेल्स कि मैंने दोनों हटा चुका हूँ ऑप्टिकल फाइबर क्लैम्प्स, बट फिर भी हमें ऑप्टिकल फाइबर शो हो रही है वहाँ पे। तो इट मीन्स कि वो वहाँ पे टूटी हुई ऑप्टिकल फाइबर पड़ी है। तो आई जस्ट क्लीन इट अप। अब मुझे सेम प्रोसेस दोबारा करना पड़ेगा क्योंकि वो ऑप्टिकल फाइबर डैमेज हो गया वहाँ से। तो अब थोड़ा सा जल्दी करते हैं इसके लिए। ट्राई टू कीप दिस क्लैम्प्स इनसाइड द मशीन ओनली, क्योंकि उसके ऊपर डस्ट पार्टिकल्स जमने का उतना ही खतरा रहता है जब तक अगर आप वो एटमॉस्फेयर में रहेगा। तो अब हम क्लैम्प खोल सकते हैं इसको एडजस्ट करने के लिए। सो दिस इज़ हाउ इट इज प्लेस अगेन। तो अब इसे भी साफ करके एक बार दोबारा से स्ट्रिप कर लेते हैं। जब तक ऑप्टिकल फाइबर बफर में है तब तक इट्स सेफ फॉर यू टू हैंडल विद योर हैंड्स, बेयर हैंड्स। बट अगर वो नहीं है, अगर वो क्लैडिंग पे आप टच कर रहे हैं, तो इट्स वेरी डिफिकल्ट कि आप बेयर हैंड से उसे पकड़ें सिर्फ। सो आप चाहे तो जब भी आप कभी स्टूडेंट्स को या किसी को प्रैक्टिकल करवाना चाहते हैं इनका, तो स्पेशली उनको स्टूडेंट्स काफ़ी रहते हैं कि उनको छेड़खानी करना पसंद है, तो वो क्या करते हैं, मोस्टली वो ऑप्टिकल फाइबर को हाथ में पकड़ के इधर उधर घूमते रहते हैं। तो इट्स वेरी हार्मफुल फॉर देम ऑल्सो कि कभी भी कोई भी प्रॉब्लम हो सकती है उसमें, कि हो सकता है कि कभी आंख में चले जाए, कुछ चले जाए, तो उन्हें गॉगल्स भी पहनवा के रखें वहाँ पे, जो स्पेशली एक्सपेरिमेंट गॉगल्स होते हैं। सो हियर आई विल क्लीव अगेन। So place the optical fiber in the V chambers. And again आप स्क्रीन में देख सकते हैं कि ऑप्टिकल फाइबर कहाँ पर है। जो ये ऑप्टिकल फाइबर टूट रही है उससे आपको पता लग गया होगा कितनी सेंसिटिव ऑप्टिकल फाइबर है ये। तो ये भी रेडी है हमारा फिर से। देन थोड़ा सा केयरफुली इसको प्लेस करेंगे अंदर। तो नाउ वी सी कि वो दोनों कैसी दिख रही है ऑप्टिकल फाइबर्स इसमें। अब वो थोड़ी सी ओवरलैप कर रही हैं ऑप्टिकल फाइबर्स, पर हम उसे एडजस्ट कर सकते हैं, वो अपने आप ही मशीन कर लेगी उसे। देन वील गिव अ स्टार्ट अगेन। ऐसा बहुत बार होता है कि आपको एरर्स इसमें शो दिखाई जाते हैं, बट कुछ होते हैं जो कैलिब्रेशन की वजह से बार बार एरर्स आते हैं, बट आपको कुछ टाइम तक दोबारा दोबारा आपको रिपीट करना पड़ता है कि वो स्प्लाइस हो जाए उसमें, क्योंकि मशीन अपनी कैलिब्रेशन के हिसाब से ही उसे प्रोड्यूस करेगी। तो वी ट्राई अगेन कि एक बार वो दोबारा से करके देखें उसे। तो अभी भी वो एरर शो कर रहा है उसमें। जितनी बारी भी आपसे नहीं होता है, इसको बार बार आपको रीसेट करना पड़ेगा सेम पोजीशन पे लेके आने के लिए। तो अभी वो नहीं कर रहा, तो हमें कोई एक ऑप्टिकल फाइबर को दोबारा से एंड प्रिपेयर करना पड़ेगा उसका, क्योंकि वो कहीं पे उसका प्रॉब्लम दिखा रहा है। तो वी हैव टू अगेन स्प्लाइस इट अप। तो यहाँ पे अब हमें वो दिखा रहा है कि वो कितना लॉस बियर कर रहा है इसके अंदर। तो हमारी दोनों ऑप्टिकल फाइबर्स प्रिपेयर्स हैं। हमें कुछ 8.7 का दिखा रहा है। इट्स रेड इन कलर, इट मीन्स कि वो हमारे लिए हार्मफुल है कि हम अब उसे ना स्प्लाइस करें। बट स्टिल वी हैव टू सी अ टेस्ट गोइंग ऑन। हम कोई फील्ड में अभी नहीं है यहाँ पे, तो इट्स ईजी फॉर अस कि हम यहाँ पे आराम से इसको स्प्लाइस कर सकते हैं। तो नाउ यू आर सीइंग मेरे पास एक गो का ऑप्शन आ रहा है अब यहाँ पे, जो पहले नहीं आ रहा था कि स्प्लाइस करने के लिए। तो टू स्प्लाइस नाउ वी हैव टू प्रेस द ओ। देन जैसे ही ओके प्रेस करते हैं उसमें इट्स आस्किंग मी कि आपको इस पे स्प्लाइस करना है या नहीं करना। तो आई एम विलिंगली स्प्लाइसिंग इट। तो आप देख सकते हैं यहाँ पे एक आर्क अभी प्रेजेंट हुआ और ये स्प्लाइस नहीं हुआ यहाँ पे। आप देख सकते हैं सबसे नीचे यहाँ पे लिखा हुआ है आर्क टू वीक। जो मैंने आपको तब भी बताया था कि वो 4 हेड्स बन जाते हैं हमारे 2 हेडेड आगे से, कि वो बल्स आउट हो जाते हैं आपस से, आउटवर्ड्स मूव हो जाते हैं। ये मोस्टली पुरानी ऑप्टिकल फाइबर मशीन्स में होता है ऐसा, क्योंकि ये कैलिब्रेशन इनका ऑप्टिकल फाइबर सिंगल मोड से मल्टी मोड, मल्टी मोड से सिंगल मोड में रहता है। तो इसकी वजह से ये थोड़ी कैलिब्रेशन में प्रॉब्लम्स आती हैं। तो इस चीज़ को ओवरकम करने के लिए हमें ऑप्टिकल फाइबर्स को दोबारा से रिपेयर करके दोबारा से इसको हमें स्प्लाइस करना पड़ता है। तो दिस वाज द प्रॉब्लम जो मैंने आपको कहा था कि पॉसिबल हुआ, तो मैं आपको दिखाऊंगा अभी। तो दिस इज हाउ इट्स रिप्रेजेंटेड इन ऑप्टिकल फाइबर। आप दोनों एंड्स को देख सकते हैं, वो बल्स आउट हो चुके हैं, एक दूसरे से दूर हो चुके हैं उसके अंदर। तो अब हमें फिर से कोई ऑप्टिकल फाइबर लेके उसके दोनों एंड्स को फिर से प्रिपेयर करना होगा। इन द मीन वाइल मैं आपको तब तक ऑप्टिकल फाइबर दिखाता हूँ जिसको हमने पहले से स्प्लाइस करके रखा हुआ है यहाँ पे। सो दिस इज द ऑप्टिकल फाइबर यहाँ पर जो है हमारे पास। हमने रेड कलर की एक ऑप्टिकल फाइबर ली थी, तो वी हैड स्प्लाइस्ड इट। जो हमारे पास यहाँ पे स्प्लाइसिंग की गई थी, उसके बाद हमने उसके ऊपर एक स्लीव चढ़ाई है। तो हमारी जो भी स्प्लाइसिंग का पार्ट था जहाँ पे सिर्फ क्लैडिंग क्लैडिंग शो हो रही थी, वो अब एक स्लीव के अंदर है। तो अब स्लीव इतनी स्ट्रांग है कि वो बेंड तक भी नहीं हो सकती है। तो हमारी जितनी भी ये स्ट्रेंथ है वो सारी की सारी वहाँ पे हमारे पास है अवेलेबल। तो क्या है कि कभी भी अगर हम इसको आगे कहीं पे भी लेके जाते हैं या कहीं पे भी ऐसी रैंडमली प्लेस कर देते हैं, तो इट्स ईजी फॉर अस कि वो हमें पता है डैमेज नहीं होगी वहाँ पर। तो व्हाट हैपेंस इज कि ये जो स्लीव्स होती हैं, जो मैंने आपको इनक्लोजर दिखाया था, इनक्लोजर में ये स्लीव्स एज इट इज प्लेस की जाती है वहाँ पे, ताकि ये ज़्यादा डिस्टर्बेंस में ना आए, क्योंकि ये बहुत ही वीक सेंसिटिव सा बॉन्ड होता है इसके बीच में, जो हमने अभी यहाँ पे स्प्लाइस करना है इसके बीच। तो इस तरह से कुछ हमारी स्प्लाइस होगी हमारी ऑप्टिकल फाइबर इसमें। तो हम एक बार दोबारा ट्राई करके देख लेते हैं इफ इट्स पॉसिबल कि हम अभी कर पाएँ इसको स्प्लाइस। आई होप कि आप सबको ये चीज़ समझ में ज़रूर आ गई होगी कि एग्जैक्टली स्प्लाइसिंग करनी कैसे है। सो साथ साथ आई वांट टू नो कि अगर आपका कोई भी डाउट है तो मैं साथ साथ वो अभी क्लियर कर पाऊँ उसके लिए। तो इट विल बी इजी फॉर मी कि मैं साथ साथ प्रिपेयर कर रहा हूँ और साथ साथ आपसे बात भी कर सकूँ इसके लिए। I'm repeating all the steps for the optical fiber preparation. So place the optical fibers again, and this time maybe it may get fuse. And again it has produced the overheads. The losses were too high that it cannot be generated to be a splicer. So we have to keep on repeating the process until we get the splicing done. At the fields, it mostly happens at many a times that a splicer technician is not able to do the splicing because of the atmosphere present over there, due to dust or due to instability of the ground. So they have to do the process again and again. So that's why a single optical splicing may take near about 20 to 30 minutes also for a single splice of a ribbon fiber also. So you need to be patient and you need to be accurate or concentrated at a single time. So if anyone have any questions till now, you can ask for me. It's still showing the same losses over here, but we'll try if it fuse it for the. It's still 8.6. This time we can see there is a splice, and it has spliced the optical fiber, and we are getting a loss. You can see over here that is 0.19 dBs. So it's a very lesser loss we are having attaining over here. So it's very useful for us also for optical fiber कि हमारे लिए वो बहुत ही easily splice होके और वो बहुत ही इतने कम लॉस पे वो काम कर रही है. सो अब इसे केयरफुली अब निकालना भी बहुत ज़रूरी है, क्योंकि इट्स इंपॉर्टेंट कि आप जब भी इसे निकालते हैं अगर तो जर्क्स लग सकते हैं इस पर, तो वो कभी भी टूट सकता है क्योंकि वो बॉन्ड बहुत ही कमज़ोर है. तो व्हाट वी नीड इज़ कि हम जो क्लैम्प्स हमने जो लगाए हुए थे, अब हम क्लैम्प्स को बाहर ना निकालें, हम क्लैम्प्स को ओपन करके ही सिर्फ और सिर्फ ऑप्टिकल फाइबर बाहर निकालें, क्योंकि क्लैम्प्स का वेट भी ऑप्टिकल फाइबर के जॉइंट को तोड़ सकता है. तो वी नीड के हम क्लैम्प्स को केयरफुली ओपन करें यहाँ पे. सो ये हमारी ऑप्टिकल फाइबर है जो स्प्लाइस हो चुकी है यहाँ से बिल्कुल सेंटर से. सो नाउ व्हाट आई विल डू इज कि मैं जो मेरे पास ये स्लीव है, स्लीव को धीरे से अपनी ऊपर की साइड पे लेकर आके और इसको एकदम सेंटर में ले आऊँगा जॉइंट को. सो आई वांट दैट जॉइंट टू बी इन द सेंटर. तो वो मैं अपनी नेकेड आई से भी देख सकता हूँ, यहाँ पे ट्रांसपेरेंट है जहाँ पर कि वो एकदम सेंटर में हो यहाँ. सो जैसे वो कभी भी सेंटर में आ जाता है तो आई जस्ट वांटेड कि मैं इनमें से कोई भी स्लीप चैम्बर ओपन करूं, कोई भी स्लीप चैम्बर ओपन करके आई कैन प्लेस दिस ऑप्टिकल फाइबर इन दिस. कोई डिफिकल्ट नहीं है, ये बहुत आराम से इस पे प्रोसीजर लिखा हुआ है कि आपको कैसे प्लेस करना है इसमें. सो जैसे ये प्लेस होती है आप स्क्रीन पे देखिएगा, मैं इसे जैसे ही क्लोज कर रहा हूँ यहाँ पे, तो इट स्टार्टेड हीटिंग इटसेल्फ। उसने बताया कि वो अपर वाले चैम्बर में है इसमें, एंड इट्स स्टार्टिंग लोडिंग इटसेल्फ, मतलब वो हीट प्रोसेसिंग में है और वहाँ पे हीट प्रोड्यूस की जा रही है इस टाइम पे। तो वो पूरा लोड होगा, उसके बाद एक फैन एग्जॉस्ट ऑन होगा ताकि जितने भी हॉटनेस वहाँ पे है वो सारी वो कूल डाउन हो जाए, कुछ भी अंदर का रेजिन चिपके ना वहाँ पे, एंड देन इट विल मेक अ साउंड लाइक बीप। तो वो बता देगा कि हमारा हीटिंग प्रोसेस पूरा कंप्लीट हो चुका है उसके अंदर। विल वेट फॉर दिस दैट साउंड। It may vary from machine to machine how much time does it take. Some takes 30 seconds, some take 90 seconds. This one take near about 30 to 35 seconds to complete and process. So here we are ready with the splice, जो उसने beep की sound करी अभी, तो it's an indication कि we can open the heater part and we can see over here कि वो पूरा tight हो चुका है वहाँ पे, and if I just touch it, it will be hot and it will be very sticky right now. So I don't have to touch it again and again. I just have to keep it aside for a few minutes and then it will be cooled down and it will be a very solid material. As you can see, there is some type of glue coming out of it from the very end of it, from both the sides. It's actually the resin inside the, you can say, the epoxy of the silica gel inside the tube. So it has been flattened all around and it cover all the optical fiber splicer inside. So it's now a very strong bond and a permanent bond and more secure bond. It cannot be broken easily now. So this is how we do the splicing part all over, and these are all the equipments we use for the splicing machines. So this is the complete set we have to perform in splicing machine. So and afterwards we'll be looking forward that how exactly we can find a fault inside an optical fiber. When optical fiber is made or installed, how can we find a fault inside an optical fiber? We'll be using a different equipment for that. We'll be going after for the next session then. So for now, for the practical purposes, this one is we are done with. So I like to like to end the session with all this. Before that, I would like to ask if you have any question regarding this practical.
No question.
Northern India, Northern India Engineering College.
Do you have any query or would you like to give any feedback?
Shri Balaji College.
No question, sir. Each and every point was very clearly explained. Thank you very much.
You're welcome, sir. ठीक है.
Lunch break करें.
Mhm. So we'll go for a lunch right now. We'll be back by 2:15. We'll be back by 2:15. Then we'll start the next session where I'll introduce you to an optical fiber technique to how to get the losses calculated and how to see the all the losses inside an optical fiber through a machine called as OTDR. So we'll be looking forward to that machine and we'll be working on that machine. So then I'll perform a practical video on that. So it will be very practical sort of a type, and I'll show videos of it regarding it, and then we'll continue with this. Okay. Then thank you so much.
normal optical fiber. Pigtail is used for the experimental purposes. If you are using an optical fiber and its strength is not more than certain strength, so you can just join the pigtail over there
ऐसे अभी आएगा मेरे को भी आ रहा है ऐसा अभी तो स्टार्टिंग हुई है ऐसी लाइन चलने का आ गया केवल हाँ मुझसे तो आ रही है हाँ तो पोस्ट अभी डाउनलोड चल रही है स्लो है हाँ चलता बन चल वापस से कर दो आंसर कैसे स्टार्टिंग किया आपने ये तो नोट बना लिया इसको कितने बार होगा इसको
Good afternoon, all the remote centers and the participants available at various engineering colleges and polytechnics. Once again, we welcome you here on the third session of today's about optical fiber communication. I hope you might have enjoyed the practical and theoretical demonstration about the splicing, and the expert Paranjit Singh will discuss in the third session about the OTDR. If your cable is broken in between, the fiber cable is broken in between, how will know where it is broken? If it is 10,000 kilometer, or it is underground or undersea. The equipment used is OTDR, and you will be able to recognize the distance from your center and the broken place to repair it. So now I request the expert, Mr. Taranjit Singh, to take this session. Taranjit Singh.
Hello everyone, welcome back for this session of your new OTDR. Yes sir, सेव है इसमें, इसी लैपटॉप में सेव है। हाँ जी हाँ जी। So before going on onto the ODR, the device which is being used to find all the faults inside, we have to go through about the various components we have to use in the optical fiber communications. There are various types of components we are using to connect the optical fiber from a receiving end to from a starting point or in between also. So there are many types of or different kinds of components we are using. So let us go through first about the components. I'll show you the image in between also. The first of all, the most important component we are using in optical fiber communication is an optical fiber. And telling about an optical fiber doesn't only stand for the meaning of two. It means that we do not have only two types of optical fiber, that is your single mode and multi-mode. We have different kinds of manufactured optical fibers in the industries. So let us go through that types of optical fibers so that you should have a clear view about the optical fibers. So these are the different types of optical fiber being manufactured for different kind or different purposes in the industry. So firstly, you can see here, you can see the zip cord. Here you can see the zip cord. It's actually containing two optical fibers, which is one is blue and one is red. So this is exactly like how a jacket zips works, that if both of them are attached to a receiver and a transmitting, and only then it will be working. So it means for one cable is always used as a secondary cable for even if you are going for a transmission from a single cable and you require a transmission from the secondary cable also, so you can have that on an instant point. You do not have to repair or something else. If one broke down, other will be still working. So this is how we use the zip cord. For making a zip cord, we require the different cables. Then afterwards, we require the Kevlar being fitted into the cables, and then afterwards the optical fiber inside that Kevlar. Then we have the distribution cable. Now, if I explain about the distribution cable, there is a very less difference between the distribution and the breakout cable. So let us start explaining first the distribution cable. Suppose we have a company called as so and so company, telecommunication company, who is actually giving the services to its customer. So what he will be doing, you have to provide a particular optical fiber link to a particular city, to a particular point, or you can say extension box where you have to deliver the services. So he's providing the similar services at the different ends. So he do not have to employed or deployed any kind of different optical fibers. What he will be doing, he will be gathering all the optical fiber in a particular one case, and he will be joining all that optical fiber to a one end, and then he will take that optical fiber throughout the city and he will distribute into the different streets. So it will be easier for him to install the optical fiber also, and easier for him to identify or to rectify, or you can say to find the faults inside a single optical fiber. So this is how we use the distribution cable. Then we have a loose tube. Loose tube I talk about later because it's not the exact structure of a loose tube. And then we talk about a breakout. So you can see a breakout cable. Now the first difference we can see from the image is that in the distribution cable we have a complete Kevlar over the optical fibers and do not have any Kevlar inside the buffer of the optical fiber. But on the other side, in the breakout, we can see we have a Kevlar over here. If you can just see over here, the white color for the complete optical fiber, and then again for the each and every optical fiber we having a Kevlar again. It is because these breakout cables are not meant for a single purpose. Means these breakouts are actually mean that the services are breaking out. All the companies can merge an optical fiber. If you suppose there is a new city being built alongside the Chandigarh, so what will be happening is that all the companies will be trying to give their services to that city. So what they plan to lower down their cost of installation of optical fiber and buying, what they do, they collaborate with each other. They particular define one, they manufacture one optical fiber only for each other. So single fiber will be to a single company, maybe 2 or 3 maybe for the company, and rest of the governments, MTNL, BSNL, or any other company can use that optical fibers. So this is how breakout is distributed throughout the city or through the different services. Even a company can also hire a breakout cable who is providing different services to the users. In India right now we are only planning for the telecommunication and internet services to the customers, but in outer countries they have started an you can say a program called as FTTH. It's known as fiber to the home. It's a new thing they are planning of. What exactly it is for, that every services you are using which is related to internet or your callings or anything, it will directly be coming or provided to your home through an optical fiber from the base where it has been generated. So all the services you are getting from this, it will be totally dependent on your optical fibers. So the link is directly maintained from one end to another end. There is no service provider in between. So it will be very helpful for the people also, because they will be getting lightning fast speed for their all the things over there. So it will be very helpful for them also. And even it has seen in the UK also. Then when this FTTH program was started, the cost of the houses is been increased by 5% now. So the people who are actually getting these programs done in their homes, their cost of the homes is increased by the 5%. So UK government is planning to cover up whole of the country with this FTTH. In India also, there are few programs which has been sanctioned for the FTTH program, and few of the companies are also looking forward for the FTTH, which means directly a fiber will be coming to your home without any you can say connection in between or any other third-party service provider in between. So it will be a kind of a lease line to you, and you will be operating all your services through a single optical fiber. So then we talk about the loose tube. This is how exactly the loose tube structure is from the upper side. Now what all we are having here is, it's the main jacket which is covering and protecting it from the outer environment. Then we are having a thick layer of the Kevlar. It's the most important thing. It's the most important thing because it is actually giving the strength to the optical fiber inside. It is absorbing all the shocks, it's absorbing all the moisture outside the atmosphere. It's not letting inside the optical fiber tubes. Then we can see a ribbon over here. This is a plastic ribbon, usually we used to wrap newspaper with it. So this ribbon is actually used to collect all the optical fibers with a pack, so that they should not scattered over the tube over there, because sometimes loose tubes having some space around the Kevlar to adjust itself. Tubes actually have to curve around, have to go a longer distance, so they sleek bends comes over there, so that it should not be completely straight and break down of its own weight. That's why they are using a ribbon fiber, so that they just collaborate and have some space inside the tube. Then they're having the multiple tubes. As you can see, they are having the multiple tubes over here in which multiple optical fibers are there. So this can be a distribution cable inside, this can be breakout cable inside. It depends upon the usage of this loose tube. It totally or same optical fibers I have shown you before, also the same optical fibers can be used inside also. It can be a single mode fiber also, it can be a multi-mode fiber also. And at the end they having a single, it can be an iron rod or aluminium rod, which is giving the strength from the center so that all the tubes do not collide with each other. So they are using an iron rod in between and around, surrounding it all the optical fiber tubes. Then there is a tight buffer. Now why it is called as tight buffer? Because we have the maximum of Kevlar over here. It is used at the times of tight buffer is used mostly at the mountainous region or a very you can say forest regions where we have to look around for the surroundings for betterment, you can say for environmental damage should not take place in the optical fiber. So we provide a tight buffer over there, and we can see multiple optical fibers again inside the tight buffer also. So we are having a different kind of optical fiber here also. It can be anything, you can say a loose tube, it can be inside the loose tube, or a distribution cable, or a zip cord, or any other cable inside the tight buffer. Then this one I have already told you about how to differentiate between a single mode and a multi-mode fiber. In single mode fiber we are having a yellow color as a jacket, and in multi-mode we are having orange color. So most of the time you are passing by your streets, or you're passing by from your roads or highways, you usually find a multi-mode fiber, which is being used by the Indian government for the plan of, even not by the even Indian government only, but the Idea, you can say Vodafone, Airtel, all of them are using the multi-mode fiber. Now the color coding I was talking about before, we are having these 12 color codings of the optical fibers. Whenever we manufacture an optical fiber, we do not just randomly give them the color. Like if I have to manufacture from tomorrow, I will not start with the white color or with the blue or aqua green color. I have to start manufacturing from coating the color of optical fiber from blue, then orange, then green. This is how the periodically it works, and this is how they have to plan it out for the optical fiber manufacturing. In a single tube we can have more than 12 also, or less than 12 also inside a particular tube. After 12 the color repeats itself. So this is important. Some says that this color coding has been given for accordance of you can say a power, for the power limitations, that blue have the maximum power to radiate, and orange have the least, and aqua has the least power to radiate inside the optical fiber. So, and some says that it has randomly have given to a color coding to a optical fiber just to differentiate between the different kinds of optical fiber, so that we do not have any confusion while splicing the optical fiber from two different optical fiber ends. So this is how the color coding goes for the optical fiber manufacturing. And then we have the connectors. Now connectors are also a main part of an optical fiber. Connectors actually carry a lot of losses in it, because we are connecting a micron millimeter, you can say micron meter cable inside a connector, which can be easily held by a human hand. So it's very difficult to put an optical fiber inside a connector and to maintain it with the proper, without any breakage. So again, connector is an important part, because we cannot switch connector from splicing everywhere, because at the transmitting end we have to use the connector, which will be connected through a device and then optical fiber. And then sometimes we have to use the amplifiers or rectifiers to regenerate the signals. So again there we have to use the devices, different devices, so the end of the optical fiber should carry the connector over there. So we have to use the connector, but there are losses, we know that. We want to switch it over, we found some of the ways to switch it over. We found a new amplifier which directly is generating the new signal or the same signal directly from light to light energy. So it is very but as I earlier told you, it is very expensive, because it is made of the element which is rarely present on earth. It is known as Ibrium. So that is not able, we are not able to use every time. So at the places we have to use the connectors and the devices which convert from light to electrical, then electrical to again then your light signals. So this is a type of connector is known as FC connector, fiber connector. This is the most commonly used for connect an optical fiber through a device, your transmitter or your receiving ends. You must have seen probes like this in your labs already with the CRO probes that you have to just curl it around and you fix an optical fiber inside an theme. Then you have an SC subscriber connector. These are most of the connectors which are directly subscribed, means they are giving a subscription of any services. Services like if you are using an internet facility through an optical fiber domains, so you will be getting a connector like this. Or suppose you are connecting to a connector where you are providing a services to a breakout sections, so you use a SC connector over there. And then you have a optical fiber connector type like lucent connectors. These are now the new modifications has been enrolled into the industry, so different kinds of connectors are being used. This one is a very simple one. You don't have to curl it up to chain it up against the connectors. You just have directly to push it in and leave the lever from top, so it will be directly connected to a particular device over there. And then we have the patch cords. We have different uses for the patch cords. Patch cords are mainly you can say used as a practical purposes, if we are having a, if we have manufactured a new role in our industry, so what we are doing is we are manufacturing about kilometers of all of the, you can say, optical fiber at once. So now if anyone comes to purchase an optical fiber, he will not test the whole part of the optical fiber because it's not easy at that time. So a part of that optical fiber will be taken out and will be connected with two patch cords. At that time, the customer will be shown this patch cord and he will be given that that you can test the properties of an optical fiber, and if you like and you matches with your properties, you can buy this rule. So this is like a sample piece for the industry, and sometimes it's also used as a practical purposes in your labs also. So now we are having a pigtail. Now for the use of pigtail, again we can use it in the labs also for different kinds of purposes to test a new roll, even because we cannot unroll the whole optical fiber. So then what we will do, we'll splice one joint from one optical fiber, and from the other part we will put the light source in it, and we can see whole of the real losses over there. And there is one more, I'll tell you through a diagram. Like we have installed this optical fiber from one building to another. Now what we are doing is we have laid this optical fiber to the till this ends. Now what we are doing is all the receiver part, this is the transmission section and this is the receiving section. So now what happens, sometimes we have to calculate the loss, or we have to just look around for any kind of requirement, any kind of you can say repairment required inside the optical fiber. So what we'll be doing is we'll attach a patch cord over here, we splice it over here, and we can take it to a length of our you can say our requirement. So here we can use the OTDR to test the losses in between. So here we can use the patch cord for this purpose, because we cannot take out this optical fiber because it is already been laid inside the earth, or you can say it's been on the pole. So this is why we use the patch cords. Next, this is the terminal box. So here we can see about the terminal box, how it is exactly works is I tell you. This is an aluminium tray here. It's a tray where we are keeping all the splicing done over here. You can see the sleeves over here. We have the different trays to place them. What happens over here, different kinds of subscriber, or you can say different kinds of optical fiber will be coming in from these connectors, will be connected over here. And then we already have this ready-made tray over here. What we'll do is we just connect the optical fiber on this connector, and this will go directly to the other part and will come out from this, and it will be collaborated into a single optical fiber and will be used for the purpose we want to use for, even it for the receiving end, even we can use for at the transmitting end also. So it's a terminal box, we call it as a terminal box. And there we have a conduit. Conduit is actually you can say a bigger membrane or a bigger tube in which we actually put all the optical fibers. This gives the extra strength beneath the surface of the earth. because there are a lot of you can say impurities or heavy materials inside there. So that's why we require this kind of conduit over there. It's a heavy polyester, made up of heavy polyester, very solid in weights also. You must have seen when there is an insulation part somewhere around your city or your streets. I must tell you, this one is the conduit over here. It's actually giving you the extra strength to the optical fiber, and here we have the buffer or the coating we were talking about. Now this is the splicing tray. This is can be purchased from the market as well, and you can make it on your own. Again, we are having a aluminium tray over here, the black color aluminium tray, and then rest of this is an optical fiber spliced and placed into a single placements. So it is easier for us also that they will not jumble up in between. It will be very easier for us that we have placed the optical fiber from one end and taking out from the other end. Now, this is the closer I was talking about. You might have seen around your cities. These are mostly hanged around the trees or in the manhole they are present. They are using it as a optical fiber splicer closer. So all the splicing which has been done by the optical fiber present over there will be induced from this side and will be taken from any one of the hole from this side. So this will be the entrance and this will be the exit. So what will be happening? The optical fiber entering from this side will be placed in these trays over here like this and will be taken out from any other hole to the other part. So this is how the splicing is being done. So I tell you why do we use this kind of a closures. Again, if we are laying an optical fiber at a stretch of 20 kilometers, we have a 20-kilometer stretch and we have a cable of 10 kilometers. So now what we're doing is we'll lay the first 10 kilometers, then by taking few part of it, we'll joining it with the other part. So to keep these joints at a particular location only, we'll be tangle them up with the enclosure and we'll put it in the manhole. So rest 10 kilometers will be completed over here. So this is how they will be working. Now this is the fiber drums. Now drums again are an essential part of an optical fiber storage, because if we are not taking care of the drums of the optical fiber, it may damage the optical fiber itself. Why so? I tell you that if we are using an drum in a storage part, we have a drum like this over here. So this is the drum over here and all the optical fiber has been rolled on this drum. So if we keep the drum like this vertically upside down, so what will be happening? All the weight of the optical fiber plus the gravity will be working over here. So all the weight on the last fiber will damage the last fiber, because it's a glass and all the glass weight will be damaging the fiber beneath it. So it's very difficult to store a cable like this. Even we have to store the cable like we have to put the drum horizontally. So all the optical fiber will be very easy to take care of. Plus we have to take care of the drums that they do not have any sharp edges or nails coming out of it, which is eventually happening in the small scale industries. They usually don't take care of these things. So these are the components we were looking, we have to go through all before the testing of an optical fiber. So next we will be going for the testing and splicing. Splicing we have already done. This is a quick review about the splicing and its equipments. Then we will be moving to the testing part. So for the testing equipment and functionality, there is the first step which we can perform in the laboratory days by using the power meters. Power meters are used to produce a particular wavelength inside them, and through a patch cord or through an optical fiber we can judge them that how much frequency, how much wavelength we are producing at the end, how much wavelength we are getting at a particular distance. So this is how we can judge about the power strength of an optical fiber, that it is capable of carrying this much of wavelength or not. Then this is an OTDR. The thing we were talking about, OTDR stands for Optical Time Domain Reflectometer. So it's a device which actually projects all the losses inside an optical fiber, which is being laid or not laid till now. So this is the device is used by the industry to locate all the faults inside an optical fiber, because it's not easy every time to each and after 10 years or 5 years we are taking out whole the optical fiber and we are testing the optical fiber in the lab. So it's easier for us just to plug the transmitter end, take it off the transmitter end and put it in the optical fiber. So at the top of the optical fiber over here, we are having a section where we can connect the optical fiber over here, and which can be of variable length. Means we cannot define, had no limitation with the length. If we are even taking off 100 kilometers, it will show the length of the 100 kilometers over here. So it's used for to measure the length and measure the losses of an optical fiber. Then this is the working of an optical OTDR. So what exactly is happening over is that it is projecting a light through it. We can vary the light wavelengths, like we can produce a laser of 850 nanometers, a power of 850 nanometers wavelength. Then we can produce near about 1310 also, and 1550 also. So a single OTDR can manage to produce these types of wavelength in an optical fiber. We can manage manually through our settings how we have to produce in a single mode or a multi mode. So what happens over here is it projects the light out, and the light will reflect back. All the light, if reflect back from a certain point, it will be showing a point, the distance, that point, that this part having a particular loss, and due to which particular loss we are having that loss. So this is how the lights reflects back from this. So I explain you optical fiber with a graph over here. Suppose this is an optical fiber already laid under the earth crust. So here we have an optical fiber starting, and this is the end, the receiving end. So now what we'll be doing is that we will be, let's suppose we are already transmitting from last 5 to 10 years, but someday we recognize that there are some certain losses coming into it. So what we saw is we saw the blue diagram of an optical fiber, how we just installed that optical fiber. So we have found it that they, at a certain point, means about 5 kilometers distance, we have a particular connector over here. So I denoted with C, and at certain point after 10 kilometers, we have a point which has been spliced. I denoted at S, and again after 5 kilometers we have again a connector over here. In the starting we have a connector, and at the end we have a connector. So now we have seen that there are losses or some power loss in the optical fiber. So what we'll be doing, we'll connect a OTDR from the transmitting end. We'll generate produce a fake output from the fake, you can say a light from it as a transmitting. So the light will start traveling from this way through the optical fiber strength. So what will be happening, wherever the connector is loose, or you can say wherever the connector actually causes the reflection part. So connector actually reflects back the light. So in the starting only OTDR will judge that there is one connector over there, and then whenever it starts moving, it show again a connector. If it's loosen up or it's break down, it will show the reflection over here, and we can see it in the graph over in the OTDR. And for the splicing, there will be no reflection losses. We have already seen that there are no reflection losses in splicing. So for this, it will show a different graph. So it will be very easier for us to judge about the splicing and the connector losses. So that's how we judge all the graph of an OTDR. So how do we obtain an OTDR graph? Though I just draw an ideal graph. It's our length, and it's a power. So this is the graph, the power versus length graph on an OTDR when we create an output or a trace of an optical domain fiber. So what happens here? It started with high power, so the graph starts from here, and in the starting only it show a loss over there. Then afterwards the power start decreasing from variable lengths, and sometimes it show a graph to upside, and then again it starts moving down. and somewhere it will show a graph to the lower side, and it will be start decreasing till the end of the fiber. Suppose this is the end of the fiber, and at the end of the fiber there will be again OTDR will be showing the losses. So now how this OTDR is working and how we can read the losses inside an OTDR. So this is a length which is near about 60 kilometers, we assume that. So we pass a 850 nanometer wavelength from this side. So first of all, we talk about this loss in the very beginning of the optical fiber. So it is actually showing an optical fiber a loss. For us, it's actually, we have already assumed that we will not consider it to be a loss, because whenever an OTDR generates a light out of it, some part, as I already told you about the relay scattering, that some part of the light try to come back, and that part is called as back scattering. And every time we produce a light from the OTDR, the light back scatter to the OTDR. So at that time, OTDR cannot judge it is because of a loss or something, or due to because it's experiencing the reflection over there. So we already know the concept that is due to the back scattering or the relay scattering. That's why we do not consider this type of losses. So this is not a loss. In about, you can say, 10 meter to 20 meter, we cannot judge in the starting, in the very beginning, we cannot judge if there are any losses or not. So we have to neglect these losses because these are not losses exactly. Then when the power start moving through the length, it's obviously it have to degrade through the graph. Then at a certain point, if we achieve a peak like this, upper peak like this, it means there is a loss due to a connector. Whenever we have a graph pointed to upwards, it means we have a loss due to a connector over here. And then again the power will be reduces. And then again, if we find a graph like this, it means the peak to the downwards, it means this is a loss due to splice. And then afterwards the graph is again decreasing and decreasing and decreasing, and at the point where the optical fiber is already done, means you can say already completed, so again it will showing a graph to us with as a loss. But we already know that the cable we were you can say going for or was checking was, we already know that it was of 60 kilometers. So we know that after 60 kilometers the losses which has been showed is due to the scattering of the light in the outer surroundings. So this is the light which is being scattered because there are still rest of the power is still there in the optical fiber. So these are the losses which is being due to the scattering of light into the air. So this is why we also neglect this as a loss. But in a industrial way, we call this as a ghost also, because we know that there is no optical fiber after 60 kilometers, but it's still showing the losses. So it means means it came eventually over there. So that's why we in industry practicals also we call as a ghost. We even in the reports we write it as a ghost after this much kilometers. So it's not only mean that ghost can occur over in the last part or after the emptiness of the optical fiber. It may occur in between also. Means like a graph, some graphs come like this, like it's going, we have a connector loss, then we have a splice loss over here, and sometimes it show in between a lot of losses, and then suddenly the power again moves in the optical fiber, and then we again have a connector loss and the power dies over here. So now we are experiencing a ghost between the optical fiber. So it doesn't mean that we have to ignore it this time. We cannot ignore it because it's in between the length of the optical fiber. Now it can be due to connector which has been loosened up, or it might carry any of the cracks over there, or there is a, even if there can be a breakdown of an optical fiber. So if an optical fiber like this, it's have a you can say a breakdown over there, it was spliced over there and it has been connected like this over there now. So the light will be traveling from here to here. Some part of the light will be able to escape from that part and will be traveling through the optical fiber, but rest of the part will be moving out from there, and rest of the part will be moving or reflected back to the OTDR. So this will show for an OTDR, it's a greater loss, and now we can see that ghost is not to be neglected. It's to be considered that because it's carrying a particular use loss over here. So which the some part over here has been already been transferred to the next optical fiber. So that's why we are saying a greater loss in power, and then afterwards it's again which of the optical fiber is being left, it's been covered up with the rest of the power over here. So this is how we uses to trace the optical fiber from the OTDR, which is very important to study because we cannot judge accordingly. If a peak's coming, okay, it's a loss, so we have to regenerate again, we have to connect the losses. Sometimes the OTDR also shows if it's showing it's a connector loss, it's even show how much loss has been made over there. It means it will also tell you the value of the losses, it can tell 1.5 dB of loss has been present over here, and due to this splice there is 0.01 dB of losses. So this means we do not have to repair these losses because these are already being done by the nature of those connector or splice, because we have already seen every time we will not be able to splice the optical fiber at 0.00 dB. So sometimes we have to bear some losses, and this is due to the splice loss, and we cannot repair it again and again because it will be carrying some certain losses at that moment. So now for the connector also 1.5 or you can say 0.5 dB we cannot repair for the connector because it have to some power have to be losing for the due to the use of connector over there. So this is how we go for all the technical part of the OTDR. So I just moving forward, before I just would like to ask if you have any query regarding anything right now. I can solve it out because later on it will be difficult. So if you are not able to understand at any instant, you can just tell me. I'll repeat that whole thing right now. Do anyone have any query regarding this? So we should start moving ahead, and I wanted to tell you that due to some calibration problems in the OTDR, we have to send it for the repairment. So we are not able to showcase our OTDR right now. We'll be showing you in the next sessions if it's possible for us in the coming next sessions. So without calibration, it would be possible for us also to show a live demo of an OTDR. So here I have a video for you where you have a live demonstration of an OTDR, how it's working and how to read all the OTDR application and losses over here.
Fiber optics for sale. In this video, I will explain what is an OTDR and its applications. OTDR stands for Optical Time Domain Reflectometer. Its name means that OTDR checks the reflected light from the fiber under test along time, shown as the yellow trace line in this picture. The fiber connected to this OTDR is called a launch cable. The launch cable is then connected to the fiber under test. I will explain why we need a launch cable a little bit later. An OTDR provides a view of the fiber link by reading the level of light that
I told you just a seconds before that we having a particular losses in the starting, means about 10 to 20 meters or even 5 meters sometimes, according to the power we are generating. So to cover up those losses, or we have to, if we have to judge according to all the optical fiber, what we are doing is we are attaching a launch cable in the starting. So we know that the launch cable length is near about 10 meters, so we are using the 10 meters for the losses only, so that we have a complete optical fiber domain coverage of the losses. So we do not have to again neglect those losses. We know that it's a launch cable and we do not require any such kind of typical losses in that.
Is reflected back from the fiber under test. There are actually two types of light being reflected back. The first type is a constant low-level reflection created by the fiber called Rayleigh backscattering. Rayleigh backscattering comes from the natural reflection and absorption of impurities inside optical fiber. When hit, some particles redirect the light in different directions, creating both signal attenuation and backscattering. The second type of reflection is called Fresnel reflection. When the light hits an abrupt change in refractive index, for example, from glass to air at a fiber connector interface, a higher amount of light is reflected back.
The Fresnel reflection is actually being denoted by the connectors we are using over there. So they exactly show the Fresnel reflections over there. So whenever you saw highest peak, it again means that you are using a connector over there, and it's a difference between the refractive indexes over there,
which can be thousands of times bigger than the Rayleigh backscattering. Fresnel reflection can be seen as spikes in OTDR trees. Examples of such reflections are connectors, mechanical splices, bulkheads, fiber bricks, or opened connectors. This illustration shows the construction of OTDR. The pulse generator generates a short electrical pulse, which drives the laser to generate a corresponding light pulse. The light pulse is coupled into the fiber under test. When some light is reflected back from the fiber, it is coupled into a photodiode by the directional coupler. This photodiode converts the light signal into electrical signal, which is then amplified and recorded. This process produces the trace as shown here. The signal sent is a short pulse that carries a certain amount of energy. A clock then precisely calculates the time of flight of the pulse, and time is converted into distance based on the speed of light in this fiber. When the pulse has entirely returned to the detector, another pulse is sent until the acquisition time is complete. So many acquisitions will be performed and averaged in a second to provide a clear picture of the link's components. There are three types of OTDRs on the market now. Laboratory OTDRs are typically used in test labs. They have extremely long range with many options. Mini OTDRs are portable and designed for field testing.
These are the types of OTDR we can find in the market, and you can see the prices all around. So again, after buying an splicing machine, you have to again spend some more money to buy to see all the losses in optical fiber. So in the starting, if you are starting a business for an optical fiber, or if you are projected into your classes also, or for the students also, in the starting it's expensive, but for the long term it's not. You don't have to keep on maintaining them like the equipments for the coaxial cable or some other cables. So it's very easy for us also to maintain it for a number of years. Means you can talk about 25 to 30 years. We can just have it without any rough use of these OTDRs or the optical fiber machines.
They have built-in screens and provide data storage as traces are collected in the field. PC-based OTDRs connect with a personal computer and operate with Windows-based software. They allow saving traces in a disk and then transfer data between computers. Generally, OTDRs are used for testing with the launch cable and may use a receive cable. The launch cable allows the OTDR to settle down after the tested pulse is sent into the fiber and provides a reference connector for the first connector on the cable to determine its loss. A receive cable may be used on the far end to allow measurements of the connector on the end of the cable. Fresnel reflectance lead to important OTDR specification known as dead zones. Dead zones are expressed in distance such as meters. A dead zone is defined as the length of time during which the detector is temporarily blinded by a high amount.
Now this is a dead zone I was talking about in the starting of an optical fiber. Whenever we project any light, we have the losses over there. That's the dead zone. Over there we cannot find any type of losses over there. So to avoid those things, so that we are not able to, if we are not able to find any kind of losses over there, what we are doing is we are attaching a launch cable over there, which will be nearly, you can say, 250 meters long or less than 250 meters long even in some of the applications. So that part is always called as the dead zone part.
The reflected light until it recovers and can read light again. Think of when you drive a car at night and you cross another car in the opposite direction. Your eyes are blinded for a short period of time. In the OTDR world, time is converted into distance. Therefore, more reflection causes the detector to take more time to recover, resulting in a longer dead zone. The most common place you see this as a problem is caused by the connector on the OTDR itself.
As you can see, the most of the losses are being due to the connectors only. In the very starting, we have a pulse launch pulse. Again, because at the starting of the optical fiber, we have a connector present over there, which is attaching with the OTDR. So we have a first loss over there, and then over here we have a second loss as a splice, and then again we are having a Fresnel reflection over here. It means again a loss due to a optical connector. So every time we are connecting a connector, it means we are eventually adding a loss to it by our own means, but it is actually necessary for all our usage, so that's why we have to go through this connectors. Then loss but no reflection indicates a fusion splice or a mechanical splice or any other located loss. So whenever the graph is steep beneath much more lower at the power level, it means it's due to a splice, or you can say a crack or a breakdown over there in the optical fiber, because these things do not create reflection. It actually make the power decays over there, and at the end of the optical fiber we again having a pulse generated, because again the reflection is done, because at the end, at the receiving part also, we are having a reflection. We are having a connector present over there.
The reflection causes an overload, which can take the equivalent of 50 meters to 1 kilometer to fully recover, depending on the OTDR design, wavelength, and the magnitude of the reflection. For this reason, most OTDR manuals suggest using a launch cable, which gives the OTDR time to recover before you start looking at the actual fiber under test. The slope of the fiber trace shows the attenuation coefficient of the fiber and is calibrated in dB per kilometer by the OTDR. Connectors and splices are called events. Both should show a loss, but connectors and mechanical splices will also show a reflective peak. The height of the peak will indicate the amount of reflections at the event, unless it is so large that it saturates the OTDR receiver. Then peak will have a flat top and a tail on the far end, indicating the receiver was overloaded. Reflective pulses can show you the resolution of the OTDR. You cannot see two events closer than is allowed by the pulse width. Generally, longer pulse widths are used to be able to see farther along the cable plant, and narrower pulses are used when high resolution is needed, although it limits the distance that OTDR can see. The next thing you must understand is OTDR resolution. The OTDR test pulses have the length in the fiber, typically 5 to 500 meters long. It cannot see features in the cable plant closer together than that. If the light pulse is too long, the pulse will be going through both events simultaneously, and OTDR cannot distinguish these two events as shown in the picture. This has been a problem with LANs or any cable plants with patch cables, as they disappear into the OTDR resolution. If the pulse is too short, it loses its energy before the fiber end, causing the backscattering level to become low to the point where the information is lost at the noise floor level. This results in inability to reach the end of the fiber. When the OTDR sends a test pulse down the cable, the big reflection from the far end comes back to the OTDR, where it shows up on the trace as an overloaded reflection. That is reflected from the OTDR interface back down to the cable for a second trip, effectively becoming a second test pulse, which is reflected back from the far end yet again, going back to the OTDR to be recorded as a second trace. If the reflections are big enough, this process can go on 3 or 4 times, each time producing a ghost event on the OTDR trace. There are 5 important parameters you need to set in OTDR: fiber type and wavelength. Choose the wavelength that you wish to use to test the fiber. Refractive index is used by the OTDR to calculate distance from measured time based on the speed of light in this fiber. Distance range. In the OTDR trace, the distance range should be at least twice the value of the cable's total length. Pulse width is the length of the light pulse that is initiated by the OTDR to travel through cables and create a trace. Longer pulse widths are effective for testing long distances, while shorter pulse widths provide higher resolution. Number of averages is the number of repetitions that OTDR will send the pulse before calculating data and creating the trace.
So these are some of the parameters we have to just do it manually before starting a test. The first one, if you have already look over here, is fiber type. Means we have to first judge the type of which type of optical fiber we are testing it. So we have to go through the planouts or the layouts which already been installed. So it will be showing that it is a single mode or a multi-mode fiber. So we have to set the settings according it, and then we have to judge the wavelength also. Then the wavelength can be 850 nanometers, 1310 or 1550 nanometers. Then after that, we have to adjust the refractive index also. We have to already know from the blueprints of the optical fiber. Distance range for practical purposes, for a longer distances, or for even for the shorter distances. If we have a cable of 20 kilometers, we will put the distance range double, or you can say the twice of the distance we already know, because it will be very helpful for us to cover up the whole length at a single trace only. Then we are having a pulse width also. Now pulse width is the width of the optical pulses going through all the optical fiber at a single movements, and the number of averages will be that how many pulses we required per second to be sent through an optical fiber, at what interval should be sent over there. So these are the particular parameters we have to set in optical fiber, and they are very easy to adjust. There are some normal keys like our telephones before, up and down parameters, then enter exit keys over there to just calibrate all this parameters.
A good place to start is 64 averages, which will give good range and fast trace acquisition.
So this is how an optical fiber works, and this is exactly we have to make a traces of an optical fiber from there. So again, I like to ask if you have any query regarding till now, so we can move forward with it.
Excuse me, sir.
Yes.
Sir, how can the pulse width affect the working of OTDR?
So sometimes happens that if we are sending any sort of a pulse from an optical fiber, so sometimes that pulse actually reflected back at the same time. So we require any other pulses to be going on to the optical fiber so that we can have a full trace of an optical fiber. We require after every after 8 milliseconds or 64 milliseconds, we require a pulse to be sent it, because we cannot just put a light through an optical fiber and we can look for the traces, because there will be a certain losses and the pulse will not be coming back. Because if we are sending a pulse from an optical fiber, it will be starting in the starting only, it will be coming back, so rest of the power will not be going afterwards. So we require a second pulse will be passing through that point. So that's why we require number of pulses to be sent. Means we cannot just put a whole light through it, we have to send it into a pulse formations.
Sir, I think the frequency of the signal is constant.
Frequency of the?
The frequency of the signal means light. The frequency is constant of this light.
Yes, sir. Frequency is totally constant. We are working on the wavelengths over here. So
how can we generate a pulse?
Yes, sir.
Sir, if we have a constant frequency signal, then what is the concept of pulse here?
So can you please repeat? Your voice is not clear.
Sir, we have constant frequency.
Yes, yes.
I think the frequency of light we are using in optical fiber is constant.
Yes, sir. The frequency.
Yes, particular bandwidth we are using.
Yes, sir. We are using a particular wavelength. That's our window we are working with on the wavelengths.
Then pulse width is also constant.
So pulse width is actually constant regarding the particular number of optical fibers. So we have to adjust according to a single mode fiber or to a multi-mode fiber. We have already have the particular points over there, which will be telling us that for the single mode fiber you have this much of pulse width, and for the multi-mode you have this much of your pulse width. So according to that only we have to judge if we are using a single mode. According to that, which has been already calibrated in your OTDR, we have to use that amount of pulse widths over there. So this is not a matter of we are using a constant frequency or not. We have to set a particular pulse width which will be sending through an optical fiber.
Sir, my question is, if the frequency is constant,
Yes,
sir,
yes.
how can we adjust the pulse width?
So the frequency is constant, but we are adjusting the pulse width according to the wavelengths varying inside. We are not using a particular wavelength only. We are using a range of a particular wavelengths. So the
So how
frequency.
then you are saying that we have to select the particular wavelength.
Yes, we are selecting a particular wavelength frequency, means a wavelength range over there. It means we are using an 850 nanometers. It will not directly putting an 850 nanometers pulse into it. It will be sending from 100 nanometers to 100 nanometers. Then afterwards, for the higher level, it will be giving us the 850 nanometers wavelength over there.
So if we can select the pulse width according to our choice, then this should not be a particular parameter for OTTR.
You can say it's not a particular parameter for an OTDR. It's actually already calibrated into it. Means you have a defined pulse width for a single mode fiber and a defined pulse width for the multi-mode fiber inside the OTDR only. Just a setting to change whenever you are a single mode or a multi-mode.
So is there any type of modulation we are using in optical fiber communication?
Modulation, we are not using any sort of a modulation inside the optical fiber. All the modulations are actually into the wireless technologies only, but in the optical fiber we are just producing a light through an single glass line, so we are not using any sort of a carrier waves or any sort of a modulation in it.
Okay, sir. Thank you.
So anyone else having any questions?
Yes, at Northern India. Northern Engineering College.
Okay, so here's a closer look for an OTDR, how exactly all the buttons and parameters we can see it through it. We have number of, over here we have number of buttons we can see, and plus it's also a touch screen. Means if you don't want to use these buttons, you can simply make changes in the parameters through touching the screen. So here it's showing a graph over here. It's same exactly if you perform a practical on an OTDR, it will be showing a graph like this to you on a single panel. So it have a lens beneath it and the power level over here. So these are the normal joystick buttons for over here. These are the simple logistics buttons over there to just change the calibration of an OTDR. And this is another sort of an OTDR which has been used in industry. It is very handy type of OTDR. The OTDRs been used in the labs or the industry are very bulky and very you can say a very heavy sets over there. And this is the handle OTDR, means it is being used in the fields nowadays. So it's very easy for an engineer to hold by the whole day and can use throughout. And having a more battery also, as you can see, it's not very colorful over here. It will produce a graph in black and white, and the other one, the previous one you have seen, it's a very colorful type and we're having a very touch screens, very sensitive screens also. So similarly, we having this OTDR to be cost near about 3 lakhs, and this handle OTDR cost near about 2.5 1.5 to 2.5 lakhs. And then again, it's a trace showing you an output of an OTDR. This is the slope we are getting through the power attenuation. This is the graph being shown through a reflection of it by an connector, and this is through a splicing. And these are the power meters which I showed you. These are the more clear view of the optical fibers power meters. So we are actually connecting a patch cord or a sample cord with the testers to judge the power capacity of the optical fibers. Now, these are some of the new equipments used in the industry nowadays, which is VFL, Visual Fault Locator. So what exactly happens is this: sometimes we buy a complete roll of an optical fiber. So what happens, we do not want to unroll it and we do not want to take it out. So what we're doing is we take this VFL, a pen like structure, and put it through a connector through an optical fiber, and it start then you can say the nanometers. It have a particular works on a particular wavelength. So whenever we just connect that and switch it on, a light will travel through an optical fiber, and at the output we can just put a power meter, receiving power meter over there, which will showing us all the power generated or all the power losses if there are any. And the more easier way if we have to do is we can switch it off the lights in the industry, or you can say in a lab, and we started using the pen over there. We can see a red light going through a hole of the spool of the optical fiber, and if any of the in the darker part, if any of the light is coming out, we can see there is a breakage in optical fiber. So it's a more easier way to check the spool of an optical fiber rather than putting into an two power meters. This is the type of two types of VFLs. One is shaped as a pen, and one is the simple one which you can have the on-off button over there. Now we having an optical continuity tester. Continuity tester is an important thing because we have to keep working on the optical fiber. So we have various types of tests over there for their low loss, interchangeability, ease of assembly. There are different kinds of losses over there present. So again, these kind of the fibers connectors we'll do the connectors more in brief afterwards. So these are the connectors again from different manufacturers also throughout the countries and throughout the different states in India also. Now this is the part for an installation. Now installation is the most important part for an optical fiber to be used in the various aspects of our daily uses. So it's we have to be very careful while installing each and every optical fiber. We'll doing this into a next session. Today we were having an OTDR practical, but eventually we are not having today. So these are whole the thing about the OTDR, how we calculate all the losses and how we are going through all the losses over here. So we cannot go through the practical. So I'll just I just want to know about any of your queries now from the previous session or from the today's sessions. So we can just carry forward for few more time towards. You can ask from the previous sessions also if you have any query regarding anything.
Yes, any center have any question or query?
So if no one is having no doubts, so I just like to just repeat the splicing process once again who have missed this part or in the previous session. So I just want to repeat the steps we have to use while splicing an optical fiber. First of all, the first step will be we have to use a sleeve, which I have already shown you in the previous session, that we have to use a sleeve over an optical fiber, so which can actually prevent, or you can prevent from damage from the splicing. So second part is we have to strip the optical fiber. We have to strip it through we have various number of optical strippers present in the market. We can use any of them, like a scissor, like one we are looking over here also. Today we use an thermal stripper. We use a thermal stripper over there, which actually automatically melt all the buffer over the optical fiber, and then afterwards the next step is we have to clean the optical fiber. Cleaning is much important because we do not want any dust particles or any absorbent to be present at the optical fiber ends, which is directly because it's the cladding outside now. So it's very important to clean it after every step. Then we are having the second process as ear cleaving process. This is how the cleaver we use the cleaver as. So inside the cleaver actually cuts the optical fiber at the 90-degree plane cut. So we require a plane cut to join the two optical fiber more accurately. So this is how we have to place. You can look over here in the first part. They are showing that it's not good because your buffer is coming over the magnetic clamps. So your accuracy will not be corrected over here. Whatever you have to do is you have to keep the clamp over this side, and the buffer should be at the back side of the clamps. And then after, we have the process as loading of the optical fiber in the splicing machine. So we have to place those magnetic clamps inside the V groove. We can see this blue parts as the V groove. This machine is actually for the single mode fiber only, not for the multi modes. So we place the optical fiber in the single mode, and we have to close it down the shutter. Now we can see in this part, this is already been loaded, all the optical fiber, and they are having the points over here. Now this kind of axis will be shown on the screen of an splicing machine, that we are having X and Y axis over here. From the X axis we can look from the downwards, and the Y axis from the upwards. It's according to the cameras present over there. So it's showing us from both the ends. It's having a clean borders, and the core is completely okay, and there is no breakage inside the optical fiber. So it's very good to you can splice again. So whenever we press the arc, when we press the arc, there is a lights squash over there in the cameras, which actually producing a large amount of energy over there to produce an arc over there. Then afterwards, at the finish, we can see there is a loss being shown by the optical fiber splicing machine, that there is 0.0 dB losses in the machine, and we can see here the splice has been done over here. Then the next step is we have to take it out the optical fiber from the machine without taking off the clamps. We just have to open the clamps over there. We have to take the sleeve onto the splicing part, and we have to put it into the heat chamber, where the temperature will be near about 400 to 800 degrees Celsius, and it will melt down all the resins into it, and will strengthen the part, strengthen the whole flexible, you can say, will strengthen the splicing part over there. So these are all the steps we have seen in the optical fiber. You can practical over here. So installation part will be going further in the next session only. On 8th of September, we'll be going for the installation part, where we'll be seeing the installation, how different types of installation are being there, and different kinds of optical fiber have been laid throughout the roads and the streets over there. So this will be all for today till now, as we are not able to perform the practical. So we are done with today. So if we again for the closing, I just ask if you have any queries or questions regarding previous session or today's session only, you can ask, and after that we can close for the seminar today. I think no one is having any doubts for today's sessions. So I think we should then meet again for the next time. Okay, thank you all for joining today, and we'll meet you again tomorrow for new sessions already been shared with you. Then I'll see you again after some time. Then till then, you hope for a good evening and good day. Okay, thank you so much for today.